good to see you. Thanks for coming. I'm Rafael. I work at Intel Open Source Technology Center. I work mostly on the Linux kernel. So the Intel Open Source Technology Center is generally concerned about adding support for some pieces of Intel technology to open source software. And that is not limited to the Linux kernel, by the way. Of course, the kernel is in the focus because you can't get very far with hardware support if you don't address the kernel in the first place. But the ODC is also active in multiple other open source projects, all over the place, like libraries, compilers, tools, virtualization support, cloud orchestrators, whatnot. So this is a lot of stuff. I work on the Linux kernel. I work mostly on the mainline Linux kernel, which is the upstream of every other kernel branches you can get from distros, device vendors, and so on. I've been contributing to the Linux kernel since 2005, which is way before I joined Intel. I've been at OTC for 6 years now. So I started in 2005. In 2009, I started to maintain some pieces of kernel code, and I acquired more of them, in the course of time, I suppose. So nowadays, I maintain the core support for ACPI in the kernel, and also I maintain the entire infrastructure for power management. That's several different subsystems that work sort of together, but not necessarily very closely. That includes the CPU idle time management subsystem that I'm going to talk about today. As a maintainer, I need to do work that many people consider as boring, which is review patches, apply them, run tests, do similar stuff. I also write code sometimes. But also, in addition to those, I need to deal with problem reports from users about different things that don't work. Obviously, in the field of power management, that's popular. It's hard to get it to work in many cases. So yeah, those problem reports often lead to improvements. Sometimes they are like small bug fixes, small but significant bug fixes. But in other cases, they actually lead to some redesigns of very core features in the kernel, and that's one of the cases. Like that is what I'm going to talk about today. But first, I need to give you some background related to that. So this is going to be about CPU idle time management. So in the first place, I need to say something about CPUs. Can you see that graphs, by the way? They're very, very light, like in a color, but I think, yeah, some pieces might be missed. No, everything should be visible. Okay. So first of all, what do I mean by CPUs? Or what is meant by CPUs in the context of CPU idle time management? So let me explain that using the diagrams in the slide. So there are 3 cases illustrated here. The chain of cells on the left-hand side in each case is memory. This is the processor, and this is a processor, and this is a processor, and there are 3 different configurations. So the first one, the first on your left, is a configuration in which the processor can only execute one program at a time. One sequence of instructions. It fetches instructions from memory, processes them one by one. Nothing happens in parallel, and everything is simple. In this case, the processor is a CPU. The second case is we have a dual core processor here with 2 independent cores. The cores are mostly independent of each other. They may share resources like caches, things like that. They may functional units. But each of them can fetch instructions from a different place, and they both execute those instructions in parallel with each other, so they are, for all practical reasons, they may be regarded as independent functional units. Okay, the third case is, and in this case, every core is a CPU, right? We have two CPUs, CPU 0, CPU 1, they map to the cores. The third case is actually more complicated, and in the third case, there are two cores still, but each of the cores can fetch instructions from two different places in memory, from two different memory locations at the same time. So this core can fetch instructions from here and from here, and this core can fetch instructions from here and from there. So they fetch a pair of instructions, like, at the same time, and then they try to execute them sort of in parallel, but not exactly, because some stages of the execution of one instruction have to be serialized with respect to the execution of the other instruction within the same core, so it is not entirely parallel. And in that case, the cores expose interfaces called hardware threads or hyperthreads if you talk about Intel processors. And those hardware threads appear to be processors that can execute a single program. But in fact, they are interfaces. And in that case, the hardware threads are the CPUs I'm talking about. So the CPU, in the context of CPU idle time management, the CPU need not be a separate functional unit. It may be just an interface exposed by a core in order to utilize its internal resources more efficiently. Okay, so that's important to remember. Yeah, so the short summary of that would be that the CPU is an entity that appears to be fetching instructions from memory and executing them from the software perspective. But it need not be like that physically in hardware. Right. Okay, so the CPUs might be either busy or idle, as illustrated by those photos, right? Okay, now I would like to change the rules of the game, okay? I know that we have question bounties. But I would like to ask the question, and yeah, I would like to ask a question, and if somebody answers it, gets a bounty, okay? So the question is this: what does it mean for a logical CPU, as described previously, to be idle in Linux? Anyone? Okay. No, that's not the right answer. I'm sorry. No? No. No, it is no.
It's
no.
not in C0.
I thought
No.
it was sleeping.
What was that? I didn't.
I thought that it's sleeping.
No.
Executing Arc CPU idle.
Close, but the right answer is actually.
Okay.
Yeah. So this is the closest one, okay. So you get a bounty. This is the closest one, and let me explain this. So in Linux, actually CPU, the being idle means having nothing to do, or having no work to do, okay? That's what idle means, no work to do. Now you have to specify how you measure work in order to say that there's no work to do, right? Because that's okay. So in Linux, CPUs are managed by the CPU scheduler, which is a piece of code here, yeah. That assigns work to CPUs. And now the units of the representation of work used by the CPU scheduler is tasks. Okay, so the CPU scheduler organizes work to be done by CPUs as tasks. And a task is a piece of code, a program with some data, with some memory containing data that the program will operate while executed, and some context that have to be loaded into the processor in order to execute that program. Okay, so these are tasks, and they are units of work, or representation of work used by the CPU scheduler. And now the tasks may or may not be runnable. A runnable task is, or a task is runnable when it can be assigned to a CPU to execute its code. If there is a CPU available in the system. Okay, the CPUs may be busy and may not be available. If a task is runnable and there is an available CPU in the system, then the task will be assigned to that CPU and it will run on it. That's a runnable task. Okay, so the CPU is idle when there are no runnable tasks that can be run on it. Okay, so for each CPU there is a queue of tasks, and some of them may be runnable. If there are no runnable tasks in that queue, the CPU is regarded as idle. Now, it is even more complicated than this, because there is a special task called an idle task, which becomes runnable when there are no other runnable tasks to run on the CPU. And that really, what it means to be idle is when the CPU is running the special idle task. Okay, the special idle task, which means that there are no other runnable tasks that can be run by the CPU. That is what means to be idle in Linux for a CPU. Idle CPUs may very well execute code. They may be, say, executing interrupt handlers, similar stuff. And I will get to that in a minute. They may also be executing other instructions. So idleness doesn't necessarily mean doing nothing at all. It only means that there's no work to do, and that means that there are no runnable tasks to run on this particular CPU. Okay. Now, if the CPU is idle, so there are no regular runnable tasks to run on it, and it started to execute the special idle task, then it may ask the hardware to enter an idle state. An idle state is a state in which some functional units of the processor are in low power states, and they draw much less power than they usually do. Okay, and if the CPU asks the processor to enter an idle state, and by the way, CPU still means a logical CPU, which might be a hardware thread. If it asks the hardware to enter an idle state, then the graph here illustrates what happens roughly. A disclaimer: this doesn't represent any real piece of hardware I know about. It's just an illustration. It's not to scale, and please do not draw any like quantitative conclusions from it. But it's to give you an idea of what happens. What happens when the processor decides to enter an idle state. So as I said before, some of its functional units will be turned off or put into low power states, say by reducing the clock rate, or maybe reducing voltage, or maybe both. Okay. So first of all, it starts to draw much more power than it does initially, because it has to prepare all the functional units to go into low power states. Then, as the units go into low power states, the power drops to a certain target level, which is the actual idle state, and the processor stays in its state for some time. And then, when it is woken up, either by an interrupt or by an equivalent event, then it powers up all the functional units that were put into low power states here, and that takes some time, obviously, and then it draws a lot of power, because this is I'll say the turn-on effect causing the power to increase significantly just for a little time and then to drop. Okay, and then it stabilizes at a certain target level, which is the performance level, the performance level required after wake up. And now, because of this peak here, and because of the slight increase in power over here, the processor has to stay for a certain amount of time in the target state in order to save any energy. Like, power is not energy, by the way. Okay, power is a rate at which energy is used or provided. So the power is not energy, and if you reduce power and then increase it like on a regular basis, like very short order, then you probably won't save any energy at all. In order to save energy, the processor has to stay for a certain time in this target state, and that is the minimum residency here. So, by the way, the time spent in the idle state is referred to as residency, and obviously there are entry and exit times involved here. The entry time is necessary to enter to get to this target level of power, and the exit time is needed to get back to the full power state or functional state at the end. So yeah, okay. Now there are two parameters used by the kernel in order to identify idle states. One parameter is called the target residency, but it is the sum of the entry time and the residency, and the minimum residency. Sorry. So the target residency is the sum of the two things here. Okay, and it means, and this is the time that has to be available for the processor to be idle in order to ask for this particular state. Okay, the other parameter is the exit latency, and this is a sum of the exit time and entry time. And this is the worst case latency from starting to go to an idle state up to the point at which the processor this CPU, can execute the next instruction. Okay, so the last instruction has been executed here, and the next instruction is executed there. And the worst case latency to get from here to there is the sum of the entry and exit periods. Okay. One thing, if something is unclear on you, or you want me to explain something in more detail or something like that, please let me know, okay? Because this is complicated stuff. I want everybody to be following. So is this clear? Any questions to that part? No questions. Okay. Yeah, that is an illustration of a processor with multiple CPUs, quad-core actually, 8 logical CPUs. And if that is an Intel processor, then the way to ask for an idle state is to use the mwait instruction in the code. So the CPU asking for an idle state has to execute the mwait instruction, or maybe not has to, but can use the mwait instruction for that. It should be a better way to say it. And then it has an argument which is a hint, and a hint argument tells the processor two ththings. First, it tells the processor how deep it can go with the power reduction. Okay, how deep how much of power can be reduced by it in the idle state. And the second, it tells the processor how much latency can be tolerated by the user, whoever it is. Okay, two things. And there are some combinations that are defined for every processor, and they have labels like C1, C2, C3, and so on. Those are referred to as C states, but really they are combinations of those two parameters that I was talking about. Okay. So now, you can say mwait C3 or mwait C2, which means that the CPU executing this instruction can tolerate a specific latency, and it will be idle for at least specific amount of time. And here, this illustrates how the processor can take that information into account. So this CPU asked for C3. This asked for C2, and this asked for C6. And that means that the core, which holds these two CPUs, or these two hyper threads or hardware threads, can go in as deep as to the C2 states at the core level. So the core can actually, the processor can actually put the core into a low power state, this core. And the state it can go to depends on what was requested here, and the shallowest request wins. Okay, so this is shallower than this, so the whole core goes into the C2 state, C2 idle state at the core level. But it also means that the processor can put the entire package containing all of those cores into a low power state of its own if the other cores are ready. Okay, and they are ready if they have requested C2 or deeper, or the larger number state. And in this particular case, that happened because everybody requested either C3 or C6, okay? And this one only requested C2. So the package can go into an idle state of its own, and that is referred to as PC2 from package C2. And 2 is because the shallowest requested state was C2. Shallowest requested, over all of the CPUs in the package, and that's why this package can go into the PC2 state. All right. So if I request C2 from my CPU, it means that I give the processor a license to go as deep as to PC2 at the package level, if the other cores have requested a C2 or deeper, okay? So is this clear? All right. And that's very important because we always want to do, so you can imagine that the package level C2 actually draws much less power and can save much more energy than the C2 at the core level. So we always want to use the deepest state that can be used. All right, this is how the hardware works. And now this is how Linux uses this functionality. This is very simple. The CPU is at the high level, okay? It's very simple. The CPU scheduler, as I said before, decides or knows when the CPU is idle and when it's not idle. If the CPU is idle, it will start executing the the code of the special idle task, which is called the idle loop, and that is illustrated in this diagram. Okay, so this is the idle loop. This is the code of the idle task, the idle loop. Of course, the CPU is initially idle. So what happens is that the scheduler invokes the CPU idle time management subsystem called CPU idle, and that subsystem decides what state to request from this logical CPU, and then it asks the hardware to go to it. This is done in 2 steps. So the decision is made by the module called the governor. And the governors are independent of architecture, platform, everything. So they are just generic. They can work with any CPU in any instruction set and so on. Okay, so these are the governors decide on what state to request. Okay, and the driver is the module that actually talks to the hardware that knows how to request the state. So obviously there needs to be a way to represent the states in a generic way, independent of the architecture and so on. So they are represented using those 2 parameters I was talking about, the target residency and exit latency. And there, for every logical CPU, there is a list of states ordered by the power that is drawn in each state, but that's usually hard to get. So they are actually ordered by the target residency, and the deeper the target residency, the higher the target residency, the deeper the state, and the less the power it will draw. All right, so the governor has a list of states it can choose from. It has those 2 parameters for every state it can use to make the decision. And then the driver translates the state representation into the hardware, the information needed by hardware to get into that state, the target state. There are 2 governors today in Linux. One is called menu, the other is called ladder. They are used in different configurations of the kernel. More about that later. On Intel, you can use 2 different drivers. The one is called Intel idle, the other is called ACPI idle. And the Intel idle driver has a list of idle states for every CPU it can run on. So the list is hard-coded in the driver. And if it recognizes the CPU, it knows what idle states it can use with it. Or rather, if it recognizes the processor, okay, the entire processor, it knows the list of states it can use for every CPU. And it will use those states. The ACPI idles driver is similar, but it takes the state information from the ACPI tables, which sometimes may be not accurate. There are drawbacks for here and there, but I'm not going to go into the. Okay, so this is the idle loop. Of course, after the state has been entered, there will be an interrupt or another wake-up event after some time. And then the scheduler has to re-evaluate if the CPU is still idle, so if there are any runnable tasks in the queue. If there are none, then again we go to the idle loop, and that goes like forever if there are no runnable tasks at all. Yeah, so far so good. Enter the scheduler tick timer. So the problem, so what is the scheduler tick timer in the first place? So the scheduler tick is a timer that runs, that triggers periodically, every once in a while, and it triggers in order to implement the time sharing strategy of the scheduler. Obviously, if there are multiple runnable tasks assigned to one CPU, they have to share the time of that CPU in order to make progress. So for that to happen, the scheduler has to interrupt those tasks if they don't release the CPUs voluntarily, which may or may not happen. And that's what the tick is for, primarily. This is the primary reason for using the tick. It is to interrupt a task that doesn't want to release the CPU on time. Okay? But this is problematic from the CPU idle time management perspective. And now, do we have any more t-shirts? Okay, so now the question is, why is this problematic for the CPU idle time management?
It will interrupt the idle cycle?
Yeah, it will interrupt the idle loop on a regular basis. T-shirt, please. Congratulations. Okay. So it will interrupt the idle loop periodically, which means that, for example, if there are idle states that are with target residencies above the tick period, they will be never used, because it doesn't make sense to ask for them. Okay. This is the first problem. The other problem is that even if there are all of the idle states have target residencies below the tick period length, it still is sometimes beneficial to stay in the deepest state for a longer time, not necessarily to wake up from it every tick. And a tick can trigger as often as every millisecond in modern kernels. So it usually is beneficial to stay, if there are no runnable tasks, we want the CPU, the processor, to really stay in the deepest idle states for longer than 1 millisecond. Okay? So there are two problems, right? One is that if we have very deep idle states, they may not be used at all with the scheduler tick running, and the other is that it will just wake up from the deepest state too often. All right. Yeah, I have spoiled a bit. Sorry. Now, of course, that problem I was talking about can be solved, because if you recall what it means to be idle for a CPU, it also means that the idle CPU doesn't need to run the scheduler tick. And of course, because there are no runnable tasks on the CPU, because it is idle, okay? So if there are no runnable tasks, then we don't need the time sharing strategy to work, because there is no need to share the time of the CPU, so why to run the tick? No reason, okay? And that's what people thought or observed, and implemented that in the kernel. Actually, this was implemented in the early 2000 years, I think. So it's been there for like 10 years or had been there, I should say, for 10 years or so in the kernel. Sure. I'm getting to this. So now people implemented something like that in the idle loop, and this is in more detail, right? The previous graph was higher level, this lower level, and that was done in Linux 4.16 and before. We changed it in 4.17. More about that later. But if you look at it, the idea was to stop the scheduler tick up front before entering the rest of the idle loop, essentially. And if the tick was stopped, then it wouldn't wake up the CPU, and everything depended on what other wake-up sources there are, and we could estimate how much time the CPU could spend in idle, and then select the appropriate state and so on. The tickless mode, getting to your question, the tickless mode is the kernel configuration in which the scheduler tick is stopped in the idle loop. And there is a full no hertz mode, which means that the tick can be stopped in other cases too. But primarily, this means that we can stop the tick here. Can. Tickless means the idle loop stops the tick. And tickful means the idle loop doesn't stop the tick. Okay, good. So tickless, again, tickless means that the idle loop stops the tick. Okay, so there are cases in which it doesn't make sense to stop the tick. Say if we know that there is a timer very short, other than the tick, then we don't need to stop the tick because the other timer will wake up the CPU anyway. But there are cases like that. But okay, so the idle loop stops the tick, then checks if the CPU is still idle. If it's still idle, then the governor is invoked, and then the driver is invoked, and then there is wake up, and then again, and on exit, the tick is restarted. All right. So do we have more T-shirts still? Good. So now the question is, there is a problem with this design, and does anyone can say what the problem is, just by looking at the?
Need someone to wake up the CPU?
Yeah, and more precisely.
If we stop tick counter, we don't get interrupt from tick. So the CPU won't be waked up.
It can be woken up by other interrupt. By another interrupt, but close. But what if the other interrupt doesn't happen short enough, right? Or soon enough? Okay, so there may not be other timer. The tick may be the only one. that we know about, okay? And there may not be other interrupts occurring anytime soon. So the CPU might actually spend too much time in the idle state that's selected by the governor.
We may configure tick time on another tick rate.
Yeah, but that is not very useful. So I will tell you how this was solved. But that really, yeah, we can give a T-shirt to.
But a follow-up question would be, so you told us previously on the previous slide that we first do estimation how much time we want to spend in that low power state.
Right.
So don't we account for that somehow? I mean,
we can, but in this design, the tick was stopped unconditionally without looking at what the governor does. So it was stopped up front. This is a problem. Okay, because if you stop the tick up front, you may not have a wake-up interrupt to wake you up because you don't know what state will be selected by the governor at this point, and that's what the problem really is with this design. Okay, so there were bug reports. So this has been there in the kernel for like 10 years. Everybody was sort of kind of happy with it. But then problem reports started to trigger about this behavior, and surprisingly enough, the first kind of problem reports were about that it is not necessary to actually stop the tick in some cases if the governor selects a shallow state, because if we know that the governor if we know that the state will be shallow or within the tick boundary, then stopping the tick up front is a waste of time, because then we know that if we expect a shallow idle duration within the tick period, then why bother stopping the tick at all? Okay, so it's just an overhead to do it. So this was the first kind of reports we got. And it doesn't look very seriously. Yeah, extra overhead in the idle loop. Well, okay. But then people in the Technical University of Dresden last year reported the problem with the other part of this problem is that if the state chosen by the governor is shallow and the tick has been stopped, then the processor can actually stay in the state for a long time and draw too much power. And that was reported last year, and that really was a trigger for the work on it, for a redesign of all that code. Because this is really bad. If you stay, say, in a very shallow state for like for seconds, you pretty much might not use the idle state at all in that case. All right. Now there is this. So this is independent of what the governor is in use even. So whatever the governor is, this will still be a problem. And by the way, if the kernel is tickless, so if the idle loop stops the tick, it will use the menu governor here. In the other cases, it will use the ladder governor. Okay, so this is the difference between the two. All right. So this is the illustration of a problem. Okay, so if the governor predicted a short idle duration, then whatever the prediction actually is, we lose in both cases. Because then, if the prediction was actually correct, then it didn't make sense to stop the tick. So we just wasted some time on all of the handling of it. If the prediction was not correct or inaccurate, then we lose because the CPU or the processor will spend too much time in the idle state selected by the governor. So that is not good, right? We lose whatever so regardless of whether the guess is right or not, we lose. Okay. Again, that is independent on the governor. And if you think about what governors do, they actually have a problem with predicting the idle duration precisely, because they have two sources of information. One source of information is predictable, and that is illustrated by the springs in the fountain here. So they go up and down on a regular basis in a predictable pattern. You can, if you look at the fountain for a certain time, you can learn how they work, and then you can predict what will happen. Okay. The other source of information is something random, which is represented by the kid running here. And you can't possibly predict anything like that. And the way and in the governor case, the first source of information is timers. So the governor knows when the next timer is going to happen because the kernel has programmed the timer, so we know exactly when the timer is going to trigger. The other source of information is other interrupts. There may be interrupts from devices, I/O stuff, everything, and they can happen at random at different situations. So actually, this has to be taken, both of those have to be taken into account when making a decision, and it is not a simple problem, because it is not deterministic. It has to be, we need to use statistics and things like that in order to predict the idle duration. Worse yet, the menu governor, which is used in the tickless case for the kernel, actually is not the simplest governor you can think about. And this diagram here is just for the illustration. I'm not going to go into details of how all of that works. The only thing I would like to say is that the time to the next timer event, which is the governor gets that time as input, is combined with the statistics collected previously in order to get a number, but that number also depends on some information from the scheduler and other things that are combined together, and then we get a predicted idle duration. Unfortunately, the menu governor has a problem problem or not, you may look at that from different angles, but the menu governor tends to predict short idle. So it amplifies the problem I was talking about, because it will tend to think that the CPU idle duration will be short for various reasons. Okay? So yeah, the menu is part of the problem. It is not the source of it, but of course, okay, right? And the solution to that was to redesign the idle loop so that the tick was not stopped up front, obviously. That's what happened in 4.17. In Linux 4.17, we actually changed the code flow in the idle loop so that the governor runs first, and then we decide whether or not to stop the tick. And actually, the governor provides the information on that. So the governor actually actually makes the decision on stopping the tick. And then the tick might have been stopped already, so in this case, it will just be handled as though it was stopped right now. And yeah, and then obviously on exit we have to restart it if it has been stopped. And now, if the governor predicts short idle, it may just say, don't stop the tick. And the idle loop will not stop the tick, and we'll just run the driver to enter the idle state. And that has there are two benefits to it. The first benefit is that if the predicted idle duration is short and the actual idle duration is short, then we will not waste the time on stopping the tick. Win. The other benefit is that, okay, if the predicted idle duration is short, but the actual idle duration is long, then the tick will play the role of a safety net. It will trigger and will wake up the CPU from the shallow state it is in, or this processor from the shallow state it is in. And now, with the resigned idle loop, the table, the results table I was showing before looks like this. So we have, if the long idle is predicted, obviously we lose if the prediction was not accurate, but we win if it is accurate. If short idle is predicted, then if the actual idle duration is short, then we win because we have avoided stopping the tick and the overhead related to it. And we may or may not lose if actually we never lose. It is like we may not win if the prediction was not correct, because if the governor predicted short idle but the actual idle period is long, then the tick is going to wake up the CPU anyway from the state the processor went into. So we won't lose in this case. Good. Okay, so now you may be interested in how this translates. This is all theory, okay? All theory. We fix the problem, and now you can ask, okay, so what about the numbers? Does it improve the numbers significantly in any way? The answer is yes, it does. I'm sorry for the display. Hopefully the green and red dots are visible. They are not on that screen. They are here, but they may. Okay, so this illustrates the idle power. And actually, this is the running average power. The running average power in a completely idle system. The green line here is without the changes I was talking about, and the red line here is with the idle changes I was talking about. Okay, so here, for example, and you may be interested also in the scale of this, because I think it is not visible. So this is 400 watts here. Yeah, 400 watts. This is 200 watts. That is 300 watts, and this is 200 watts, okay? And this is 100, and this is 200. So these are the numbers we are talking about. So you can see that this is 0 in all cases. The x-axis is at 0 in all cases. So you can see that the relative benefit and there are server systems in the Intel Power Lab. Many CPUs, multi-socket, and big systems. So here, 20% of idle power reduction. It is not running something, idle power reduction, okay? And this is 10%, something like that. Okay. I will get to why this happened actually, but yeah, more pretty graphs. So, okay. Do I still have some?
Yeah, maybe 3 minutes.
3 minutes, okay, cool. So this is one of the systems I was showing before, and actually with details. So every dot in this graph represents a single event, single wake up. And as you can see, there are like this graph, and that is before the changes, that is after the changes, okay? So you can see that this graph is very noisy. The idle durations are in the range of 300 watts to 450 even, sometimes. 300 watts is the power floor of the system. It can't possibly draw less power than 300 watts. This is a very big, fat server with quad CPUs and multiple other devices. So 300 watts. Okay, so you can see that this is very noisy. And the reason why, we have analyzed this, and it turned out that there was some instrumentation running. Some instrumentation just looking at the power draw and other things on a regular basis. And that instrumentation was sufficient to drive the menu governor into thinking that the idle durations will be short, and it will predictably, in that case, it will predictably underestimate the idle duration. And this is the reason for the random pattern of wake-ups in this graph. Now with the changes I was talking about, this noise goes away and we have a little of it, but not that much. And at 300 watts, actually this is 300 and this is 300. This is a different scale. So that's the whole story of it. There are some changes under development. I was hoping to be able to talk about that, but I have no time, so that you can talk to me about that in the hallway. And that's all. If there are more questions, now it's time to ask them.
Thanks for your talk. How does the scheme, idle scheme, works with regards to virtual extensions?
You mean
VM entry, and when you have
virtual? So in VMs?
Yeah.
So
like on KVM.
Well, basically, in order to save any energy at all of the VMs have to be idle.
But if VM decides, the kernel in the VM decides it should be idle, does it translate somehow to the host?
I think it does. I'm not sure how. So it depends on what the idle driver running on this VM has in the table of idle states. I'm not sure if they don't use the original idle state. I think they use C1 or maybe something else. So with VMs it actually affects the idle time management in a way that the list of available idle states in a VM is different from the list of available idle states in a host. And the translation is not, as far as I can say. I have to admit that I have not been following this very closely, but yeah. So if you run VMs, they will affect the idle management in a way that it will just draw more power over time.
Thanks.
More questions?
You mentioned at some point that being in a very low power state for a long time, it might draw much more energy than even in some
not
other
low power,
states.
but shallow. In shallow idle state, meaning that the governor may have a choice between a shallow state, which is high power, and a deep state, which is low power. Okay, so for example, let me go back to the slide with the. With this. So for example, in here, the processor may decide to, if the CPU requested C2 instead of C6, the whole processor can go into the PC2 state at the package level instead of PC6. Now PC6 is much deeper, so it causes the processor to draw much less power. So the PC6 is preferable every time it can be used. But if by mistake we cause the CPU to request C2 instead of C6, then it will not be reached at all.
So your point was if we may stay in C2 state for like 1 millisecond and then switch to deeper power saving state like C6 for another 1 millisecond, it will be much more beneficial. That will spend
actually not like that. So what we want to avoid is to staying in C2 for like a second, for example, or a long time, relatively long time. Okay. And that's why it is actually makes sense to run the tick if we select C2, because then if we stay in PC2, like say the CPU requested.
So basically, C2 will be tick will be required to do re-evaluation of our possible power state, right?
No, so the tick will just wake up the CPU and the idle loop will run again, and we'll re-evaluate.
That's how we will do that re-evaluation again.
Yeah,
and probably go to the deeper state.
Yeah, and we may choose to go to a deeper state. Yes.
Okay. Thanks.
Yeah.
And probably another question, if I can ask. Isn't it possible for Intel CPUs to set different power states to different parts of IC, like different cores, separately?
Yeah, but these are the core C states I was talking about, core C2 and core C3. At the core level, every core can be in a different low power state. But the hierarchy is two-level in this case. The one is the cores and the other is the package. And we also want the package. We always want the package to go as deep as possible, as deep as possible, essentially, right? Because that is where the real savings are happening.
So what is the relationship then between core power state and package power state? So we don't mess with per core power states at all.
So the relationship depends. It all depends on what is requested. If C2 is requested, it gives the license to the core to go to the C2 state at the core level, and it gives the license to the package to go to the PC2 at the package level. Okay, so now what happens at the package level depends on what the other cores did or do in the future. Okay, so if they all requested C2 or deeper, then the package can go into PC2. If they all requested C3 or deeper, then the package can go into PC3 and so on. But the two levels are they are not independent. But what happens on the shallower level, like on the higher level, determines what can happen on the deeper level, subject to coordination. Does that explain things? No? Yeah, we can talk about that.
There's the next question then.
And I have one more question. How do the changes apply for all microarchitectures since Nihil?
Oh yeah, that's a good question. Actually, they apply, so the changes I was talking about apply to everyone, not just to Intel. So this code is run by every tickless kernel in the world, like Android, and the only way to opt out is to just disable CPU idle time management, which is not a good idea. And if you want to talk about that, we can talk in the hallway. But anyway, that you can't really opt out from running this code. So everybody is affected by it.
So we get improvements everywhere.
Yeah, that's basically that's a good summary. Yep.
Thank you, and probably the last one.
Thank you for your talk. Actually, I heard that these deep, I don't know how to call them, sleep states or idle states.
Idle states,
probably.
yeah.
How do they map to other power management, standby, suspend?
Yeah, okay, so this is idle, opportunistic idle. So when as I said before, when there are no runnable tasks to run on a CPU, it is regarded as idle, and that happens at runtime. So this is opportunistic as it may or may not happen while you are running the workload, right? So depends on the workload. If your workload is a text editor or an Office application, then it very often will be idle because you will be thinking about what to write and so on. On a server, your workload may be a database, and it will run on multiple CPUs at the same time for a long time. So it depends. So this is opportunistic, and it happens when it puts the CPUs into low power states if that's possible. Now the sleep states, so standby, suspend, and so on, are not not opportunistic. They are sort of forced. So you decide when the system has to go into one of them by closing a laptop leaf or similar.
I just thought that power management used different nomenclature, so to speak, like S0, S1, maybe D0.
Yeah, so this is
maybe I'm mixing things up.
This is the ACPI terminology for system sleep states. S0, S1, and so on. C0, C1, and so on is the terminology for CPU idle states, or what can be requested by CPUs.
Third question.
I'm
So we got out of time, so
to.
probably we can continue out on the discussion zone. And now let's go to the try to make a common picture for those who want. And thank you very much, Rafael, for your presentation.
If there is one more T-shirt,
Yes.
I want it to go to the friend over there in the yellow.
Okay.
Yeah.
Okay.
Yellow.
Thank you.